Okay, can everyone see my screen?
Yes, ma'am.
Yes, ma'am.
Okay, so my first portion constituted all this. You don't need to know brief history or anything, but you must start your studies. I mean, definition and properties of wavefronts, all of you know from the other portions that you have, but you must start your study from Huygens principles. Okay. This was just for introductory purpose. So all this, of course, you won't be getting into. Uh, Definition of wave, types of wave. These are also these are almost like general knowledge for you at this stage. It should be like a general knowledge. You know the definition of a wave. You know what are harmonic waves. You know what wavelength, frequency, etc. these are. This is one thing that you need to remember, that the expression of a plane progressive wave that we come across represents any kind of electromagnetic wave, not only visible light. And since it has, this is the portion a sine kx minus omega t. Someone has his microphone unmuted. Please mute your microphone. There are some disturbances coming in. So it has a unique frequency and unique wavelength, and by monochromatic we mean mono means single and chroma means color. So when we use this expression in our analytics, it will mean that we are talking about monochromatic waves. All right, but just again for your information that this the range of frequencies can be from as short as 10 to the power minus 13 to as large as 10 to the power 6, and only in between from 400 to 750 nanometers is the visible range. So all our experiments that we do in the lab is within this portion, namely 4893 angstroms, that is the yellow light. Okay. Light is an electromagnetic wave, and this is important, that there is an electric field and there is a magnetic field. And if you remember that when we analyze Young's double slit or diffraction or anything, we use the electric portion of the light. Okay. Okay, so this is the, and these are some definitions that you need to know, like what is a wavefront, what is a ray of light. When you are drawing a ray of light, what does it actually mean? So it is the imaginary line along the direction of propagation. What is a wavefront? A wavefront is the locus of all points for which the phase of vibration is the same. So when we are drawing the wavefronts in Huygens principle, you need to know what the wavefronts actually are. Then what are the shapes of a wavefront? They can be, usually if you have a point source, then you have spherical wavefront spreading out in all directions. If you have a linear source, then you have cylindrical wavefronts. You might have parallel wavefronts. Okay, for a parallel beam of light, you will have parallel wavefronts which propagate in a particular direction. Then comes Huygens principle. This is the concept of Huygens principle is very important, because it is by using Huygens principles that um, Young explained his experimental observation, and for the first time he established experimentally that light is a form of wave. Okay, so what does Huygens principle? This is very important. Okay, um, what are the three main points of Huygens principle? First, every point on a propagating wave front serves as a source of secondary wavelets. So this this blue line is a is a primary wave, and see, I have drawn small black dots on this primary wave. There are of course several such black dots, but I've drawn some of them, and each such dot acts as a source of a secondary wave, which are called wavelets. Small waves, so called wavelets. Okay. These secondary wavelets travel with the same velocity and frequency as the primary wave, so that at any later point of time, if you draw the envelope to the secondary wavelets, then you get the actual wavefront at that point of time. So I've shown one for a spherical wavefront and one for a plane wavefront. What is actually happening using Huygens construction. Okay. Of course, Huygens did not say anything about the other portion, like if wavelets are generated in the forward direction, they should also be wavelets generated in the backward direction. He didn't say anything about that, and that is a flaw in his theory. But then Young uses only the forward direction, and he could explain the observations. Using Huygens construction, you can prove the law of diffraction, as has been explained here. You can read through. I don't need to. I mean, this is very elementary. So Snell's law is explained using Huygens principle. You can see the wave fronts are drawn, and the rays are representing the direction. So this is law of refraction from Huygens principle, and this is the law of deflection using Huygens construction. Okay, both can be proved using Huygens constructions alone. And then this is very important. This is very important concept, the concept of coherence. What is coherence? And if you remember that, we'll see that for observing interference patterns, it is a necessity that the sources must be coherent. Otherwise, you will not be able to observe any interference pattern. Why that is important, that is also there in the later slides. So what is coherent? You can see that this is incoherent waves, and this is example of coherent waves. You can clearly see that the incoherent waves are moving forward, but there is no relation between them. They are moving forward each in their own pace and manner. On the other hand, coherent waves have a particular pattern, and all of them follow the same pattern. Particularly, you can see that the phase, see, if this is the crest, then all the waves have the crest in the same position. If this is the trough, then all the troughs have the same position, which is not the case with incoherent waves. So you can obviously see that the phase relation is important for a group of waves to be called coherent or incoherent. So this is the definition. A wave is said to be perfectly coherent if it appears to be purely sinusoidal for an infinite period of time or infinitely extended space. Two sources are called coherent if they have a constant phase relationship, same frequency and waveform. Okay. So I gave you three examples to show what perfect coherence or incoherence means. Here I have shown what exactly perfect coherence means. See, all of them are marching with the same phase. There is no difference in their positions, the positions of their feet. This, on the other hand, is total incoherence. There is no relation between the people moving around in this region. Everyone is moving his or her own way. So this is total incoherence. And this, I would say, is partial coherence, because they are moving in a particular direction. All of them are moving in one particular direction. However, their individual hands or feet are not exactly in sync with one another. So this is the example of partial coherence. Okay. So coherence may be temporal or spatial. Temporal coherence tells us what is the monochromaticity of a source. How monochromatic can you call a source to be? So it is a measure of the correlation of the light's wave phase at different points along the direction of propagation, and you measure it by a parameter called coherence time. The distance traversed by the wave in the interval of coherence time is called coherence length. Okay. So a monochromatic wave ideally has infinite coherence time. So it is perfectly correlated for all time. White light would be incoherent because it has a large range of frequencies. White light is composite light, so there is a large range of frequency. Okay. The product of the range of frequency delta f and coherence time tau c is always 1. And then there is spatial coherence. So it is mutual interdependence or connection of variable wave quantities. So if two or more waves are moving together, then you define something called coherent area, which is defined like this, where d is the diameter of the source and capital D is the distance from the source. So using this, you can see how spatially coherent a particular group of wave is. Okay. So these two are again very, very important definitions. Now let's move on to our next, that is interference. Any question from the last slide? Coherence, etc., Huygens principles. Any questions? Okay, then from there, the two most important things that you need to learn up are Huygens principles and coherence. Okay, these two are very, very important. And next comes interference. So what is interference? First of all, you need to, in order to study or analyze interference, you need to know first what is the principle of superposition. Okay, and the principle of superposition is the same as we had done in vectors or the chapter of forces in our high school. It's that the resultant displacement produced at a point by a number of waves is the vector sum or algebraic sum of the displacements produced by them individually. Okay, so in two cartoons I have tried to explain what this means. In first, we have two pulses rather, which are moving towards each other. They have different amplitudes. Okay, so when they superpose on each other at one point, then what happens is their amplitudes add up, and at the point of superposition we have an amplitude which is larger than each one of them. Okay, algebraic sum, and after superposition they just move in their own directions without being affected by one another. The second part, we have two pulses once again moving towards each other, but now they have opposite directions of amplitude and their amplitudes are equal and opposite. So what will happen at the point of superposition? Here we have the algebraic sum x plus minus x, which is 0. So here the amplitude will be 0. They nullify each other. and then once they cross the point of superposition, they move ahead with their original amplitude. So this is a very important diagram related to principle of superposition, and you need to understand this very well. And I suppose that if you understand these two figures, then you don't need to learn by rote what superposition is. You will understand what superposition is. Okay. So if you have the displacement at a position due to a wave as y1 and another position due to another wave as y2, then if these two waves superpose at the point of superposition, the resultant displacement will be y1 plus minus y2. So it will be either add, addition, or it will be either sum or difference. Okay, the sign will matter. And remember, this is applicable only when they superpose. That is, only when the two waves are crossing each other at a particular point simultaneously. Otherwise, they do not have any effect on one another. Understanding this is very important. All right. Okay. And next, we need to know the relation between amplitude and intensity. I am not going through the derivation. Just remember that intensity is always amplitude squared. Okay. So we have now three things. We know Huygens principle. We know that by principle of superposition, at the point of superposition, you have to algebraically add the two amplitudes, and intensity at a point is the square of the amplitude. Okay. So now this is the formal definition of interference. But it was demonstrated for light waves by Thomas Young. First experimental evidence of wave nature of light. And interference can be of two kinds: division of wavefront and division of amplitude. So first we go through division of wavefront. Before that, we have to understand why is it difficult to observe interference of light. Because with sound, observing interference is not very difficult. We are very acquainted with waxing and waning of sound when two or more sources are simultaneously playing. We are experiencing two or more sources of sound playing simultaneously all the time in our daily lives. But even if you have two or more sources of light on in your room, you will not see interference patterns like Young observed. Right? Why is that? This is a very important question. See, suppose you have two such sources and you have a double slit, one slit in front of each source, and you have a screen. So if you expect to see interference pattern on the screen, you will not. You will just see the two patches of light due to the two sources. So why is it that we are not observing interference? It is because we have to understand why light is emitted from a source. It is emitted due to transition of atoms from their excited to their ground state, and this happens for an interval of 10 to the power minus 9 seconds. Okay. Whereas optical pulses are of the order of 10 to the power 15 per second frequency. So such a short pulse, one optical pulse of frequency 10 to the power 15 per second, would contain a million oscillations like this. Okay. So light coming from different sources will have, even if you switch two sources of light exactly at the same time, even then they will have a fixed phase relation only for about 10 to the power 9 second. So even if they form an interference pattern, that would stay for only about 1 billionth of a second, which of course we can't see. The resolution of observing two separate events by our eyes is at least 10 to the power minus 1. Okay. Hence, interference pattern due to light coming from two separate sources cannot be observed. So once again I am repeating, as I did in our original classes, that if you are asked this question, that if there are two separate sources of light, will there be interference of light? Your question will be, yes, there will be interference of light, but we will not be able to observe because each pattern would last for about 1/100000th of a second. So to our eyes, such patterns do not come as separate entities, separate events. For us, all we see are bright patches. We do not see the interference pattern. So then, how do we see an interference pattern? In order to do so, we have to have sources which has a constant phase relationship over a very long interval of time. That is, we must have coherent sources. Okay. So Young's experiment did this. He used coherent sources. How? He used one single source from which light was made to go through a single slit, and then he had two slits, and since each point on the wavefront according to Huygens is a source of secondary wavelets, so these points on the slits, they acted as sources of secondary wavelets, and these secondary wavefronts therefore travel forward, which produced the interference pattern on the screen because they are derived from a single source and hence they are coherent. Okay, so this portion again, the mathematics of Young's double slit experiment is important, but this portion of why it was for the first time that he overcame this difficulty and produced four coherent sources. How did he produce coherent waves? That is also very important. Okay, so we have a single source, two slits, each act as sources of coherent waves. So if any one slit is covered, the pattern on the screen disappears, showing that the two sources act as coherent sources. So this is the experiment that shows interference by division of wavefront, because a single wavefront is getting divided into two wavefronts by the two slits. All right. Wavefronts from S0 reach the slits S1 and S2, and according to Huygens principles, they are sources of secondary wavelets. So the points lying at S1 and S2 send out secondary wavelets. These wavelets, having originated from a single wave, are coherent. The secondary wavelets interfere by superposing on each other, and thus they produce a pattern which are known as the interference fringe pattern. As you can see on the screen, we have alternate dark and bright lines which are the interference fringe pattern. So since a single wavefront has been split up to produce two wavefronts that interfere, this is categorized as interference by division of wavefront. Okay? The two sources S1 and S2, the two slits rather, they act as virtually coherent sources. Another important question. Why are S1 and S2 called virtually coherent sources? Answer is, they are not actual sources, they are just slits, but they act as the positions of generation of secondary wavelets according to Huygens principle. And these secondary wavelets are originating from a single wavefront coming through S0. So they are coherent. Therefore, here in our experiment, S1 and S2 are not mere slits, they act as the sources, but they are virtual sources and coherent sources. Clear to everybody up to here? Because after this the mathematics will begin. Clear up to here? Okay,
Yes, ma'am. Yes, ma'am.
so I'll move on. Now the intensity distribution will be studied. This is the schematic diagram. Earlier diagrams were all experimental setups. Okay, this or the previous page. This is the schematic diagram for the mathematical analysis. S1 and S2 are the virtually coherent sources. D, small d, is the distance between them. One ray travels from S1 towards P, a point on the screen. Another ray travels from S2 to the point P on the screen. Capital D is the distance from the midpoint of S1, S2 to the midpoint of the screen at PO. Okay. E1 is the electric field produced at the point P due to the wavefront coming from S1, and E2 is the same for the wavefront coming from S2. Okay. This must be maintained. D must be much smaller than capital D. This is very important. So we write down the mathematical expressions of E1 and E2. We already discussed why, how the electromagnetic wave is expressed mathematically, either as a sine function or a cosine function. So E1 and E2 superpose at the point P. So we apply principle of superposition and get the resultant field E at the position P. Okay, remember, we take only the I direction. Why? Because capital D is very large compared to small d. So this screen is very far away. So virtually they are traveling in the same direction. And so we know that to get the intensity, we have to get the square of the amplitude. So we've got the resultant field. We have to take the square of its modulus in order to get the intensity at any point P on the screen. So we do the mathematics. I hope I don't have to explain the mathematics now. We've used for this portion 2 cos A cos B equal to cos A plus B plus cos A minus B. So we have this expression of the intensity. Even from this mathematical intensity expression of the intensity, we cannot say anything about the result on the screen because we do not understand anything. There are still cosine functions in the expression of intensity. So we try to incorporate the practical situation where the frequency of the optical beam is about 10 to the power 15 per second. So all terms with time will vary 10 to the power 15 times per second. So for the observer, we have to take a time average of such frequently changing parameters, and taking the time average, we see that average of cos square term is half, whereas average of cos theta term is 0. So in this expression, we have two terms giving us half. We have two cosine square terms, each will contribute half, and the cosine term containing omega t will give you 0. Of course, this last term does not contain omega t, so it will remain as it is. So using this, our final for intensity is something like this: I1 plus I2 plus 2 root over I1 I2 cosine phi. This expression you must remember. Okay, this is a very simple derivation. This might come in the exam. I'm not saying it will come, but this is a derivation that might come for 4 marks or so. But more important is this expression. You need to remember this expression: I equal to I1 plus I2 plus 2 root over I1 I2 cos phi, where I1, I2 are intensities due to the two sources, and phi is the phase difference between the superposing waves. Alright, this is very important. So how do we get the maxima and minima? You can clearly see that the intensity term is governed by the cosine term. Others are constants, so only phi will change according to the position of P on the screen. So the value of cos phi will change. Now the maximum of cos phi can be plus or minus plus 1, and minimum can be minus 1. So for maxima, that is cos phi is plus 1, you get maximum intensity as this root I1 plus root I2 square, where cos phi is plus 1, so phi equal to 2 n phi. 2 n pi, you put the value of phi, you get this expression. So the condition for getting maxima is path difference S2p minus S1p equal to n lambda. Okay, this is the condition for constructive interference. Very, very important question. From the expression of intensity in Young's double slit experiment, derive the condition of constructive and destructive interference. Very, very important, typical question, university question. Okay, from the expression of intensity, derive the condition of constructive and destructive interference. So this is the condition for constructive interference, and for minima, again you put cos phi equal to minus 1, so phi equal to 2n plus 1 pi, and from here you get path difference is n plus half lambda. So this is the condition for destructive interference. Alright. You can see that if I1 is equal to I2, then I is I max, which is equal to 2I, and I min is equal to 0. So when this happens, then we can see that I by I0 is a cosine square term, so that the fringe pattern will be like this. This is the intensity distribution graph. You can see intensity remains constant at cos square phi. It is either 0 or a high, I0. Alright, depending on the value of the path difference. And this is the pattern that you actually see on screen. So now we are at a position to write down the conditions for sustained interference. First and foremost, sources must be coherent. Second, capital D much greater than D, so that we can use the mathematical analysis that we did over here. Sources must be equidistant from either slit. S1s equal to S2s, otherwise path difference will be there before they start their journey from S1 and S2. Source must be monochromatic, otherwise we will not be able to use the expression mathematically as we did. For very high contrast, I1 equal to I2 is necessary. And finally, the sources must be in the same state of polarization. We cannot do this experiment with polarized light. Okay to everybody? Up to here, is it? I hope it's okay. So this is more or less Young's double slit. After this, we have some calculations, that is calculation of fringe width. Okay, so again we have the same schematic diagram of ydse. Young's double slit experiment is in short form called ydse. So you calculate the fringe width. We saw the fringes are of this form. This is the form of the fringes. So you can see that there are alternate dark and bright fringes. We now intend to calculate the fringe width. Very simple mathematics, simple Pythagoras theorem. From the figure you can see that, okay, let us go to the triangle. If you take this triangle in red over here, S1P Q, then you get S1P square is equal to S1Q square plus QP square, which is equal to D square plus Yn minus D by 2 whole square. And then you take the next triangle, S2PR, there you get S2P square equal to, again, capital D square plus Yn plus D by 2 whole square. So S2P square minus S1P square would give you something like this, 2YND. So S2P square minus S1P square is of course S2P plus S1P into S2P minus S1P. So I have written that down. 2ynd divided by s2p plus s1p. Now we have to remember that capital D much greater than small d, so s2p almost equal to s1p, which is equal to d. Now you might say that if this is the case, then this becomes 0, but we do not do that, because that difference s2p minus s1p, no matter how small it is the reason for the interference fringes to develop. So we cannot neglect it no matter how small it is. But the sum we can easily write as twice d. Okay, this is again very important concept. So s2p minus s1p is 2ynd by 2 capital D, or yn. Okay. So the path difference is this, delta equal to ynd by d. And this is the phase difference, 2 pi by lambda ynd by d. So for constructive interference, we know path difference is equal to n lambda. So ynd by d is n lambda. So yn is n lambda capital D by d. So the distance of the nth bright fringe from the central fringe is this. So you see, for the central fringe, it is 0. For the first bright fringe, it is lambda d by d. For the second bright fringe, it is 2 lambda d by d, and so on. Separation between two fringes is yn plus 1 minus yn, and it is lambda capital T by d. Okay, fringe width for bright fringes. For destructive interference, we have delta equal to n plus half lambda. So yn d by d is n plus half lambda. So this is the distance of nth dark fringe from the central fringe. So at 0, you get the first dark fringe. Remember, y0 for bright fringe was the central fringe, but for dark fringe, y0 gives you the first dark fringe. y1 gives you the second dark fringe, y2 gives you the third dark fringe, and so on. And this is important to understand, because in numerical, if it is written that so and so is the position of the third dark fringe, then you have to remember to take y2 and not y3. Whereas if it is said so and so is the position of the third bright fringe, then you take y3 directly. Okay, so you have to remember this in order to solve problems. And separation between two consecutive fringes is once again lambda capital T by d. So fringe width for dark fringes is lambda capital D by d. So we can clearly see that beta bright equal to beta dark equal to lambda capital D by d. Alright. So all the fringes are of equal thickness. In Young's double slit experiment, the fringes are all of equal width. These are also called fringes of equal width. How are the fringes oriented? If you have horizontal slits, then you have horizontal fringes. If you have vertical slits, you have vertical fringes. Shape of fringes. We know this is the intensity pattern on the screen, alternate bright and dark bands. But actually, the shape is like this. So actual shape is obtained as rectangular hyperbola. However, screen is very far away, so we observe only the straight region, this middle portion, the straight region of the rectangular hyperbola. Okay. Locus of an arbitrary point P on the two-dimensional screen is given by this. This is again very simple mathematics. You can use simple trigonometry and show that this is the case. Another very important concept and again very important question is redistribution of energy. Okay, this is the fringe pattern in ydse, alternate dark and bright fringes. Bright fringe means enhanced intensity, which in turn means enhanced energy. Dark fringe means reduced intensity, which means reduced energy. So, If energy is reduced, where does the energy go? If energy is increased, from where does the energy come? This is a very, very important question. You see, if you take the expression of intensity in ydse, and then if you take the average of this expression, the average comes out to be I1 plus I2, which means that the average intensity equals the total incident intensity. So even though intensity is lesser at some regions and more at some regions, and we know that for high contrast, we prefer intensity to be 0 in the dark regions and brightest at the bright regions. So the average intensity but equals the incident intensity. So total intensity energy is conserved. So there is no question of destruction of energy. Energy disappearing at the positions of dark fringes reappear at the position of bright fringes. So this is known as distribution of energy. This again is an important concept and is an important question. It comes, what do you mean by redistribution of energy in intensity? Clear? Very, very important question. Okay, finally, this is a problem which I am not reading out. Sum, and you can go through it and see what it says. How, if you place a small transparent sheet in front of any one of the slits, how the fringes shift, and how using this formula you can find out the width of a transparent material whose width cannot be otherwise obtainable using our daily instruments. If it is thick enough, we can measure it with if it is thick enough, we can measure it with a screw gauge or slide caliper. But if it is a very thin transparent material like very thin glass or very thin mica sheet, you cannot use your mechanical devices. So we use this optical method to find the thickness. All right. And mathematics is very important. After this comes another experiment showing division of wavefront, which is Lloyd's single mirror. These are just for your knowledge purpose. The analytics are not very important. So you just know, there might be a question that apart from Young's double slit, what are the other devices that shows division of wavefront? So this is how Lloyd's single mirror uses division of wavefront. The red ray comes from the source and the blue ray comes to the screen directly from the source, and the red ray comes to the screen after getting reflected from the mirror. So these two then form a pair of coherent sources and produce interference fringes. Okay, this is an explanation of Lloyd's single mirror. And then there's Fresnel biprism. Okay. What is a biprism? I have written what is a biprism. What happens in biprism? Setup, optical bench, single source, eyepiece, and diffracting edge is kept parallel to the slit. Okay, I'm not going into the details because again this is an experiment that you need to know because this was there in your practical syllabus. You can read through, I have explained it in detail. This is the kind of fringe that you get. Okay, and this is the fringe width. So that more or less covers interference due to division of wavefront. So we are left with interference due to division of amplitude and Fraunhofer diffraction, the two overviews that you need. So what I'll do is next week, let me check the calendar.